So this is a topic about analog to digital conversion using voltage to time conversion. That is A to D converter, which is used for an voltage to time conversion. So generally an analog signal can be converted into a digital signal by counting the pulses from variable frequency sources, and its frequency is going to be dependent only on that particular analog input signal value. So this counting is done only for the fixed period of time, and alternatively the pulses from a fixed frequency source can be counted for a variable period of time, and the time period is then dependent on analog signal which is under conversion. And this is a simple block diagram which is to show the basic voltage to time conversion type of A to D converter. So here we can see an integrator, a comparator circuit, and then we have a counter. And this is a clock pulse which is measured for a time period of Tc, and this is the analog voltage which we are going to pass, and we are going to get the output in terms of binary, that is the digital output. So it is possible to make A to D converter by counting the cycles of a fixed frequency source for a variable period. So for this, analog voltage required to be converted to a proportional time period. So this is an elaborate diagram which is shown with the gate present. So this is the AND gate combination, and we have the sample and hold circuit which is to sample the values of your analog voltage and then pass it on to the next stage. So, and we have a high speed counter which is to count the number of clock pulses too. So that functional block diagram explanation, where we saw a sample and hold circuit, an voltage comparator, and a high speed counter. And we also had something called as a negative reference voltage which is called as VR. So this reference voltage is applied to the integrator, and that is going to integrate the voltage VR, and it is going to provide a positive polarity output. So this is the integrator, and the integrating factor is going to be tau is equal to R into C. Okay, so then the analog input signal which is under conversion is named as Vi of t. So that will be sampled, as I said earlier, by the sample and hold unit. And we have a control voltage which is a fixed value, and the sampled at any instant of Vi is applied as an input into a non-inverting terminal of the comparator. So this is the non-inverting terminal, and this is the inverting terminal of the comparator. So here only we are going to feed in the value. So the integrator output is Vs, and that is connected to the inverting terminal of the comparator. So here is a Vs which is connected to the inverting terminal, and this is what is the Vi, the input analog voltage that is getting sampled from the sample and hold unit, and that is fed into the non-inverting terminal. So this is how we get the waveforms. So with respect to the voltage VR that is applied into the integrator, and that is connected to the inverting terminal we saw now, and the output of the comparator is at 1 as long as the output of the integrator V0 is less than VA. So this is the condition. So when the time at a particular time instant, say for example t is equal to t, the VC value will go low and the switch will remain open. So when the enable signal, that is the VEN, goes high, the switch will be closed, and thereby the discharging of a capacitor takes place. Also the NAND gate is disabled, and the waveforms are just shown as here. So we have an integrated voltage Vs is less than an analog voltage sample Vi as shown in the output graph. So the comparator output is at positive saturation, or it will be at logic 1. So this is the control voltage which is at logic 1. So a fixed frequency clock, that is the VCL, is applied to a high speed counter, and that is through the AND gate G. And the AND gate is enabled for the duration when t is equal to 0 and when Vi is equal to 0 to the time. So until the fixed time t is equal to a particular time instant, from then to 0 to t it is going to be enabled. So when your Vs is equal to Vi, so we know that Vs is equal to VR into T divided by tau, because the time constant is given. I showed this for an integrator circuit. Tau is equal to R into C. So therefore, at the time t is equal to a particular time instant capital T, then Vs is equal to Vi, and we can infer that the particular time instant value is nothing but tau into Vi divided by Vr, because we have substituted Vs is equal to Vi. So from this, it has got reduced to this particular value. So this is the actual input and output waveforms for the Vc value and the Vg value and the available clock pulses which is applied to the circuit. And assuming that the clock frequency Fc is going to be the clock frequency, then the output count is taken as n, that is obtained during the time interval of 0 to t. So that is, I told you, t is equal to 0 till the fixed time interval whatever we are taking. So from the time 0 to the particular time, it is given by n is equal to Fc into t. Fc is the clock frequency. So now we know the value of t from the previous equation, that is, here we have obtained the value of t, so that we get it substituted here. So the sample and hold circuit samples the positive input voltage and for the every time instant t. So the sampled voltage is held for the time duration. So held is the circuit is going to hold that particular value for a time duration of th. So during the period of th, the switch is going to be opened, and then the integrator will operate with its output following a ramp voltage. So when Vs is less than Vi, the comparator output Vg is at logic 1 and the gate is enabled with Vc in 0 state. So this is going to continue for a time interval of whatever is the fixed time interval of t, and then during this time the clock pulses are passed by the gate. So that is what we are showing, even the gate voltage as a high during the high value of the control voltage. So the gate will also be enabled and Vc is with Vc in 0 state. So this continues for a time interval t, and during this time the clock pulses are passed by the gate to a high speed counter. So during the time interval Ta, the gate is disabled and the digital output is read from the counter. So the switch is closed during Ta and the capacitor discharges, resetting this value Vs, this voltage, to the 0 volt. Thus, it will start again newly a new conversion will start. So this is how the loop repeats itself for the every given input analog voltage. Thank you.